So we are now come to it, the bewildering idea of a chance-driven computation. This idea has fueled a cottage industry of methods, chance-based, which percolate through the landscape. And we have the catch-all phrase, the Monte Carlo method, to capture this ensemble of ideas. But we're jumping ahead of ourselves. Let's come back and summarize our key discoveries so far. The problem: we are given a bounded function of d variables, let us say, on the unit cube. And let's say the function is bounded in absolute value by 1. We wish to compute its integral, a number fixed but unknown at this point that we're going to call j. So we want to compute or estimate j. Our process is going to involve a random selection of a point in the d-dimensional cube and an evaluation of the function at that point. Of course, this gives us a chance-driven evaluation of the function. No matter. So what have we discovered? That the expected value of the function evaluated at a random point is precisely the parameter j that we are seeking, and that the expected squared spread of the function value around its center, the variance, is bounded by unit. We're immediately now led to the idea of generating a random sample by independent selection from the unit cube in d dimensions. In other words, I get a sequence of points. Now notice the virtues of vector notation. Each boldface uppercase x represents a collection of d variables. But I'm going to do this experiment n times independently, so we have repeated independent trials. Each of these vectors is a unique trial in its own right. We need to identify which trial. So let's use now superscripts, because subscripts are getting overloaded. So a superscript 1 indicates the first trial, a superscript 2 indicates the second trial, and a superscript n indicates the nth trial. I'm going to think about n as a modest number, thousands, tens of thousands, a million perhaps, but not much larger. And of course, even a million evaluations of a function is not very much for a modern-day computer. You can do it in a trice. Right? So we are going to start with a random sample, x1 through xn, with the same underlying distribution as a random x chosen from the unit cube. And what do we do next? Naturally, we evaluate the value of the function. We look it up at each of these n randomly chosen points. And let's call the values that result y1, y2 through y sub n. Now, what can we say about these derived values y1 through yn? What do we know about them? Well, each y depends upon a unique x, and the x's are drawn independently, and therefore we immediately conclude that y1 through yn represents a random sample, a sequence obtained by repeated independent trials of some experiment. The experiment at hand, of course, relies upon random selection from the unit cube and then evaluating the value of the function at various points. Moreover, these values y1 through yn have a common distribution. Why? Because, of course, the x's have the same underlying uniform distribution on the unit cube. And therefore, all the y's have expectation exactly j. And all the y's have variance no more than unit. Okay. And the moment we've got an independent sample like this, we know immediately that a law of large numbers beckons invitingly to us. So what is the law of large numbers going to say in this context? Well, first, we want to form a sum of the values y. Of course, these are just a sum of the values of the function which is given to us at fixed but random points 1 through n. Okay, so you pick x1 through xn randomly, evaluate the function at those points, and add up the values you get. That is all it is. And let's use our old notation again. Let's call this S sub n, an accumulated sum of function values. But expectation is additive, and therefore the expectation of this sum is naturally just the sum of the individual expectations. But each y has got a common expectation j, and therefore the expectation of the sum is simply n times j. What can we say about the variance? Well, the variance of Sn is likewise a sum of the individual variances, because we know that y1 through yn are independent variables. Each of the variances is bounded above by unit, and therefore the variance of Sn is no more than n times unit, or simply n. And a law of large numbers immediately tells us that the sample mean Sn over n is going to be concentrated near its expectation, which is exactly j. And so now we have a principled estimate of j by the underlying sample mean from this process. Sn over n should behave like j. This procedure at its heart is what we today call the Monte Carlo method. So where does the Monte Carlo method arise from? Where does the name arise from? The story is possibly apocryphal, but it goes that von Neumann, one of the originators of the method, was amused by the chance-driven context for this. He said, we are going to get at a fixed value, an integral, by essentially gambling, by a game of chance. And the connotations of the gambling houses at Monte Carlo with games of chance led to him suggesting the name Monte Carlo for the method. And ever since then, we call such methods which rely upon computation using random generations of points, we call all of these Monte Carlo methods. Now, this is all well and good, but naturally one of the questions we would ask is, well, we want to evaluate a j for some mysterious purpose in physics or somewhere else, and you're saying, well, play this mysterious game of chance, compute a sample mean, divide by n, and that's an estimate of your underlying unknown j. How good exactly is this estimate? Let's take a prompt look at this. Right. So, our basic question is, how well does a sample mean estimate the parameter j, the integral that we are trying to estimate? Well, we're going to follow the same path as before. First, let us specify an error tolerance that we are willing to sustain. Say we are willing to sustain a 10% error, perhaps a 5% error, a 3% error, maybe a 1% error. Well, of course, we don't want to a priori restrict what error tolerance should be. So we'll inevitably call the amount of error in j that we're willing to tolerate, we'll call it epsilon. And so our basic question will be, what is the probability that the sample mean Sn over n deviates from its expectation, the fixed but unknown j, in absolute value by more than epsilon? In other words, you are beyond error tolerance. We would like this chance to be small. Of course, we recognize the structure of the analysis. This is going to follow exactly the process by which we analyzed poles, by which we derived the law of large numbers. Right. We begin by clearing the denominator, multiply throughout by n, and so this expression becomes equivalent to saying this is the probability that Sn deviates from n times j in absolute value by more than n times epsilon. N times j is just the expectation of Sn. And now Chebyshev's inequality beckons invitingly to us. We know that this probability is bounded above by the variance of Sn divided by the square of the deviation. The deviation here is n times epsilon, so the square of that is n squared epsilon squared. We have an estimate for the variance. Well, we haven't computed it exactly, but we know that the variance of Sn is bounded above by n. And so the inequality keeps going in the proper direction. The probability of a deviation by epsilon or more is no more than n over n squared epsilon squared. What have we got here? Okay. Now, what do we want? Remember, epsilon is the tolerance to error that we have presupposed. So we want an error of larger than epsilon with a small probability. that is going to be our confidence parameter. So, for example, we want, let's say, an error of no more than 3% with a confidence of 95%, which means that exceeding 3% should have odds or chances of no more than 5%. If the right-hand side of an expression does not exceed 5%, then I can guarantee a confidence of 95%. Of course, I don't want to prescribe what the confidence in your pronouncement needs to be a priori. It's going to be dictated by the needs of the problem. Right? So more generally, we're going to presuppose a given error tolerance epsilon. We are allowed to make a mistake up till epsilon. But we understand there's a chance-driven game. There's a chance that this might happen, that we get a large error, more than epsilon. We'll require a confidence that the error is no more than epsilon to be, say, within 1 minus delta. Delta is a confidence parameter. This is also given to us ahead of time. And now we've got a very simple observation. If the right-hand side, 1 over n epsilon squared, does not exceed delta, then immediately we can conclude that the sample mean is going to estimate the fixed but mysterious and unknown j with an error of no more than epsilon and a confidence of at least 1 minus delta. Rewrite our expression, our inequality, and we find that the sample size needed to estimate j with an error of no more than epsilon and a confidence of at least 1 minus delta is no more than 1 over epsilon squared times delta. Let's put in some numbers here to get a feeling for what's going on. Right? Suppose we want an error estimate which gives you a fairly tight tolerance of, say, no more than 1% error. And you want a confidence of quite high, say 99%. Epsilon is 0.01 and delta is also 0.01. We plug it into our equation and we find that n needs to be only 1,000,000. If you sample 1,000,000 points at random inside the unit cube, evaluate the function of those 1,000,000 points, add them up and divide by 1,000,000, the law of large numbers guarantees that your sample mean estimates that unknown integral j with an error of no more than 1% and a confidence of 99%. Isn't that remarkable? Remember, when d was 200, we started with an apparently intractable problem. It needed 10 to the power 95 computations for a crude computation using an elementary form of Simpson's rule. Now we are saying, forget 10 to the power 95, I just need 1,000,000 computations. Of course, 1,000,000 is nothing for a modern computer. You've now apparently solved an intractable problem, but there are some caveats.